Okay, in this lecture, we're going to do some analysis comparisons and try our hand at trying to determine among different functions, which ones of them grow faster. So that's what we're doing. The premise here is that you're going to have two algorithms, A and B, that do exactly the same thing, serve the same purpose, but they have different running time characteristics. And so let's imagine that we have actually 6 different versions of these. And for each of these pairs, so this is a pair, this is a pair, and so on, for each of these rows, what I want you to do is identify within each runtime, so this is a runtime and this is a runtime, what is the dominant term. So here between n cubed and 2n squared, what's the dominant term? And for here, between 100n squared and 1000, what's the dominant term? And then use those dominant terms to compare these two algorithms on that row and determine which one's faster, okay? So I would encourage you to pause the video at this point and work through these examples yourself before we go through the answers, okay? So go ahead and pause the video and try to compare each of these across A and B. All right, I'm assuming you're done with that now. So moving on, let's compare n cubed plus 2n squared versus 100n squared plus 1000. Okay, the dominant terms here are n cubed and 100n squared. And you can tell this because n cubed grows faster than n squared. We can ignore that 2 there. And n squared grows faster than 1000, and we don't really care about that 100 either. Okay, so in terms of what grows faster between these two or these two as n grows, clearly n cubed is going to grow faster than n squared, and n squared is going to grow faster than a constant. So let's look at what these actually look like for different values, ranges of n. When n is small, okay, so n up to 10, then the a function is growing like this, right? This is t sub a, and b function is up here. So it looks like b is growing quicker. And indeed it is for small values of n. But when we look at larger values of n, and remember we care more about large values of n when we're thinking about analysis, around about n of 100, you can see that there's a crossing point right here where the a function takes over and is dominating from then on, which is not a surprise because n cubed grows faster than n squared, right? So this grows faster than this. So what did you have down? I hope you had that A is growing faster than B, or another way of thinking about that is that algorithm B is faster than algorithm A for large values of n. Okay, let's look at the second row. We had n to the 0.1 versus log of n. And another way, if you're not used to thinking about n to the 0.1, this is the 10th root of n. So if you take, the square root, this is the 10th root. So in other words, what value would this be? What value would you have to multiply times 10 itself 10 times to get n? Okay. So it might be unclear here which term dominates. So what could we do? Well, we could do a little math. Okay. What if we raised both terms to the 10th power? Well, n to the 0.1 to the 10th power, we know that we can multiply these terms together, so we get n to the 1, right? So this is just n to the 10th power, n to the 1, n to the 0.1 to the 10th power is equal to n. And then log of n raised to the 10th power is just log to the power 10 of n. And we've seen this comparison before in the last lecture, right? Or in previous lecture, we know that n is dominating a log to the power to a constant power of n. Okay, so when n is small, so n up to 100, say, notice that the n to the 0.1, right, is down here, and this is log of n. But if we punch this up, if we punch n up to a much larger value, notice that this is a very large value of n. This is 10 to the 16th. In other words, 1 followed by 16 zeros, right? Dot, 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 dot. Then what happens is eventually this n to the 0.1 grows more quickly. It just takes until we get to a very large value of n. So it is true that log of n is equal to little o, or big O, of n to the 0.1. So two ways of thinking about this. N to the 0.1 is growing more quickly than log of n, or log of n is the faster algorithm than n to the 0.1. Okay, here's another one, n plus 100 n to the 0.1, or 2n plus 10 log n. And the dominant terms here are actually this term and this term, and we can ignore these terms. And when you look at these two terms that dominate, how would you compare them in terms of their growth rates? Well, when n is small, it looks like 2n is, the a function is growing faster than the b function, okay? But as n grows really large, up to 1,000, then again, a is being dominated by b. But there's a catch here. This is actually a trick question. Notice that this is a linear growth rate, and this is also a linear growth rate, right? And we know that these are both linear because the dominant terms are n and 2n, which both grow linearly. And if we ignore the constant coefficient, which is 2, then we would say that these actually both grow at the same rate, okay? Low order terms don't matter, so 100 n to the 0.1 doesn't matter, 10 log n doesn't matter, and the constant coefficients don't matter. So in actuality, we'd say n equals, or we could say that t of n, t sub a of n, is equal to big theta of t sub b of n, right? They grow at the same rate. Even though this one's growing, b is growing twice as fast for large values of n, we ignore that constant coefficient. So again, this is kind of a trick question. We can easily identify the dominant terms, but then recognizing that they grow at the same rate, asymptotically speaking, is the important point here. Okay, let's look at the fourth one. 5n to the fifth versus n factorial. Well, there's only one term here for each. So obviously 5n to the fifth dominates and n factorial dominates within each function. And for small n, notice n less than or equal to 5, it looks like 5n to the fifth, that's here, is growing very quickly. But as you might know, factorial growth is really fast. And so all we have to do is we have to look at n of 20 and look at how fast this grows, right? Suddenly, the factorial function takes off and the 5n to the fifth is left in its dust. It can't keep up. So again, one way to think about this is n factorial dominates 5n to the fifth, or 5n to the fifth is a much faster algorithm than n factorial. Okay, here's a more complicated set of functions. We have, well, a simpler one on the right. We have 1,000 n to the 15th, which is the only term, and 2 to the power n divided by 100 n to the 15th. And so the only real question here is, which of these two things grows more quickly? 2 to the power n or 100 n to the 15th? Well, this is exponential growth. This is polynomial growth. And if you've done your reading, you know that exponential growth is always going to be quicker than polynomial growth for exponentials with a base larger than 1 for large values of n. So that's the question. Which value dominates, the numerator or the denominator? And of course, the exponential does, right? So the growth of function a is still down here for values up to 10, right? It doesn't look like it's going anywhere. And that's because while this exponential is going to grow quickly, for low values of n, this is actually dominating, okay, for small values of n. So a, this function a, is stuck way down here, while this function b is growing rather quickly, okay? But it's as we go up to larger values of n, like up to 300, notice that the exponential 2 to the n takes off and dominates from then on. Okay, so clearly this exponential is the key thing to worry about here. This almost doesn't matter for this doesn't really matter for large values of n, and exponential growth certainly grows faster than polynomial growth. Okay, last one, and this one looks difficult, and I gave it to you just to help you reason about things a little bit more carefully. We have 8 to the power 2 log n plus 1000n versus n to the 7th. Okay, now the first thing that you know that n to the 7th is the only term here. So what about this? 8 to the 2 log n versus 1000n. Which one grows more quickly? Well, it looks like 8 to the 2 log n grows more quickly than 1000n because it looks like there's an n in the exponent, which there is. So does this have exponential growth? Well, no, not exactly. Okay, it's strange to have a logarithm in the exponent. Is it exponential growth? Well, let's see what happens when we try to simplify it. 8 to the power 2 log n. Let's assume that this logarithm is base 2. So log is log base 2 of n, okay? Then if we replace 8 with 2 to the third, which is the same value, then we have 2 to the third, all to the power 2 log n. Well, we can combine 3 and 2 by multiplying them together. So we get 2 to the 6 log n, and again, that's log base 2. And we can bring this 6 over here to be a power of n. So we have 2 to the log base 2 of n to the 6th, okay? And we know by our log rules that 2 to the power log base 2 of something is that something. So this is equal to n to the 6th. So which is growing faster, 8 to the 2 log n or 1000n? Well, clearly 8 to the 2 log n is exactly equal to n to the 6th if the logarithm is base 2. And n to the 6th is actually growing more slowly than n to the 7th, okay? So all that to say, even though this looks like exponential growth, it's actually polynomial, okay? So that just because you have an n in the exponent doesn't mean that it's exponential growth, because that logarithm makes that n grow very slowly, okay? So here are the graphs for this function, or these two functions rather. A, which is this, is growing like this, and it looks like it's growing faster for small values of n, very small values of n. But as n grows up to 100, right, then b takes over, because b is n to the 7th, whereas a is more like n to the 6th. Okay, so I hope that this was instructive to you to see how we can compare different functions. And if you want to get a feel for how two functions behave, you could always plot them. And remember, what we care about are not the values for small values of n, the function growth for small values of n, but for large values of n. That's what we really care about when we're comparing which term dominates in analysis.